gives you, how many 25s have you got? 16. Gives you 2 25s plus 14 25s, 16 25s, minus 7 times 57. I had to check, take a moment to check that that was actually correct. And now we'll get rid of the 25, which is 196 minus 3 times 57. So that's 16 times 196 minus 3 times 57 minus 7 times 57 at the bottom. So we finally get 16 times 196 minus 48 and 7 is 55 times 57, and if you get out your calculator, that is correct. And so your 1 is expressed as 16, just remember, forget all the middle bit, 1 is equal to 16 times 196 minus 55 times 57. So just to emphasize, this procedure is called the Euclidean algorithm, and what does it do? It finds the greatest common divisor of any two numbers, and it can be used to express that number as the greatest common divisor as a linear combination. And it's this Euclidean property, or even more precise, the fact that the greatest common divisor can be expressed as a linear combination, that leads to unique factorization. And it's important to realize that the remainder has to be smaller in some sense than the divisor in the a equals qb plus r. Okay, so that's with integers, but you can apply this to other things. What's another sort of system in which you can divide and get a quotient and a remainder? Polynomials. Indeed. And is your remainder smaller than the divisor? In what sense is it smaller? The highest power, of which is called the degree of the polynomial. So the degree of the remainder is less than the degree of the divisor. So polynomials can have the Euclidean property, and therefore you can do all of these things. There's one thing you have to remark about the coefficients. Remember, when you do, I'm certainly not going to try and do a polynomial long division on the board, but when you do it for yourself, what do you remember how you do polynomial long division? You need to look at the coefficient of the divisor, and then see how many times does that go into the highest coefficient that you've got left. So you have to be able to divide by the coefficients, by whatever non-zero coefficient. So you can divide polynomials and you get the Euclidean property for polynomials as long as you allow divisibility by every non-zero coefficient. That's to say, as long as you're working in the reals or the rationals, but it won't work in the integers. You can't always do a Euclidean division to get a quotient and a remainder if you restrict yourself to integer quotients. So that's just a bit of a subtlety again.
If the integer coefficients are a subset of the rationals, then how do the rationals work but the integers don't work?
Because the inverse, you need to divide. You can't, if you divide by 2, you don't get an integer.
Okay.
That's the important thing.
So
okay.
All subsequent, sub-polynomials have to have.
All your you mustn't restrict your coefficients to the integers, because you must do a full division. We'll come back to that later.
There's no limitation on that the starting coefficients have to be rational. It can't be integers.
No, of course they can be.
Okay.
Integers are rational numbers.
Okay.
With denominator 1.
Okay.
So I've given you a couple of examples to try just for yourself, if you feel strong, I think I said. because it's pretty boring. Though what might be more fun is to write a spreadsheet. All you need, you can detach the coefficients. So think of a polynomial as just a string of coefficients. And then you can look at, with this string of coefficients as your A and this string of coefficients as your divisor B, go through the procedure. It's more fun writing a spreadsheet than doing a numerical example by hand. Another set of examples of number system that I would like you to think about, that I've given you in your exercises, is what are called the quadratic integers. Suppose you take some number that is not a perfect square, and you take integers and then include, sticking into the bowl, mixing bowl, this square root of this number d's. And then you get expressions of the form m plus n times root d, where the square, obviously root d is an irrational number. Perhaps not obviously, but it will be. D is not a perfect square. And those are fascinating number systems that include all the integers, obviously, but include these certain irrational numbers, and they have very interesting properties. Some of them have the Euclidean property, some of them do not. Gauss, a very famous German mathematician, he was particularly interested in the number system z root minus 1. So introducing the imaginary number, the square root of minus 1. So all integers, you then include the square root of minus 1, and because you need to add and multiply them, you'll get all expressions of the form m plus n times the square root of minus 1. And those are called the Gaussian integers, but you can add the square root of 2 instead of the square root of minus. Many of them, and I've got some exercises on that for you to look at. And so some of them are Euclidean, some are not. Some have unique factorization. All the Euclidean ones obviously do have unique factorization. Some do not. And I've given you an example of where unique factorization can fail. Well, going back to our example, we showed that those two numbers had greatest common divisor, with highest common factor equal to 1. And notice I use the notation GCD brackets AB. Some people just write brackets A comma B. But that has so many other meanings that I think it's a bit confusing. So I always put in the word GCD, because it is a function of the two numbers. Anyway, if the greatest common divisor is 1, then the numbers are said to be co-prime or relatively prime. They're prime with respect to each other. They don't have any common factors. And so the expression that the two numbers are co-prime means immediately, if you see that in a question, then the immediate response, the knee-jerk response or Pavlovian response, must be you write SA plus TB equals 1, because that is the necessary and sufficient condition for a number to be co-prime. Greatest common divisor is 1, therefore SA plus TB equals 1 for suitable numbers S and T that you can find by this procedure. And one of the things that was studied by Euler, the famous Swiss mathematician, preceding Gauss, was how many numbers are there? Choose a number, positive integer A, how many numbers less than A are co-prime to A? And he called that number of co-prime, he called it phi of A, and that's called Euler's phi function. So phi of A is the number of integers B such that 1 less than or equal to B, less than or equal to, if you like, A, and coprime GCD of AB equals 1. And that is denoted by phi of A, and it has many interesting properties. We'll come back to that many times in this talk if time permits. So we've talked then about numbers being co-prime. But what do we mean by or normally mean by a prime number? Come on, you all know. Is somebody bold enough to say so?
A number greater than 1 that has 2 factors.
A number
Greater than 1 that only has 2 factors.
only has 2 factors.
Yes.
If you say it only has 2 factors, then you can even say it doesn't have to be greater than 1. Because 1 has only got 1 factor. So